Here at the Leibniz-Institut IVW in Kaiserslautern, we work on topics that are especially important for the areas of energy, climate, environment, mobility and health. We can make enormous contributions with composites. Compared to conventional materials, we save precious resources. Our composites are extremely durable. Thermoplastic-based fiber composites can be easily recycled. Hydrogen pressure tanks made of fiber composites will enable emission-free flying and driving. We engineer composite structures from scratch up to tested prototypes, in the digital world as well as in reality. In our laboratories, we are already working on the composites of the next generation. For processing technology, we are creating the basic understanding today that is necessary to enable to produce practically with zero waste in the future, with extremely high process speeds and very cost efficiently. We can already process thermoplastic continuous fiber reinforced tape at speeds of up to 4 meters per second. This results in high performance components for future applications.
Realistic multi-physics simulations of the material and equipment during the manufacturing process helps us optimize tooling geometries, blank holder configurations and forces, as well as processing parameters well before any tooling makes its way to the machining table or any real manufacturing takes place. The example shown here considers an aircraft fuselage strut, where a thermoforming simulation is carried out to predict any manufacturing defects such as wrinkling and folds, along with the fiber orientation and resulting component warpage. Combining this with the data available from the different sensors on the equipment and even linking and communicating with the machines allows material characterization, in situ quality control and validation of the simulations to take place and moves us closer towards complete process digitalization.
One important strategy for increasing the efficiency of fiber composites is process hybridization and material hybridization in combination with automation. Through the design of filigree load-optimized endless fiber structures, which can be overmolded or encapsulated with injection molding material with discontinuous fiber reinforcement, the use of materials and thus the costs can be optimized. The start is to use so-called organosheets that can be used in this process, here as endless fiber reinforced materials. However, the approach pursued at the IVW goes one step further, so that tape materials and all 3D printed structures with continuous fiber reinforcement are used here. The core requirement for the optimized use of continuously and discontinuously fiber reinforced materials is topology optimization and process simulation, as well as the understanding of the material properties, of course. These process and material combinations, together with process automation, lead to processes that are considerably cheaper but also suitable for large-scale production.
Our new Langzauner press here at Leibniz-Institut for Composite Materials is a central element for polymer composite research and development work. It is parallel controlled with a maximum press force of 2,500 tons and a tool clamping area of 2 × 3 meters in square. The press is supplemented by an infrared radiator field unit and a bolt-on injection machine. This enables processing of both thermoset and thermoplastic composite materials. From sheet molding compound SMC and long fiber reinforced thermoplastic materials LFT up to continuous fiber reinforced materials. We can do research work with all kinds of thermoplastic materials, from bio-based ones up to high performance materials like polyether ether ketone. In and online thermography measurement enable the determination of the material temperature, simultaneously illustrated on a control display for our operator. A complete set of all important process data such as speeds, temperatures, forces, etc. recorded at different positions is the basis for deep process understanding, process digitalization and finally process optimization.
composite materials have outstanding properties, for example, high stiffness and strength combined with low weight of the material. These properties depend to a large extent on their microstructure, for example, the distribution and the arrangement of the reinforcing fibers in the material. Therefore, for the development of better materials or more efficient manufacturing process, one needs a microscope that can look deep inside the material. Here at IVW, we have a 3D X-ray microscope, one of the most modern computed X-ray tomographs, which gives us this possibility. This enables us to simultaneously image not only individual fibers, but also their distribution in the entire composite. The data we generate serves as the basis for digital twins, for example, for modeling material properties over many orders of magnitude in the length scale.